Hello everyone, in this tutorial you're going to learn about the hyperelastic material in Abaqus. So first of all, I hope that you know a little bit about the hyperelastic material, because I'm going to just briefly explain these material and the difference between a normal material. So generally speaking, the material behaves differently in real life. So for instance, in a ductile material, what we have a clear linear curve, and it reaches the yield point, and that's basically a place that the plastic deformation starts, and it goes to UTS, and finally we'll have a failure. And on the other hand, when we have a brittle material, normally it goes up linearly, and when it reaches the yield point, we have a sudden failure. So we don't have a large plastic deformation due to the nature of the brittle material, such as brittle adhesive epoxies. This type of material normally fails immediately at the yield point, or a little bit after yield point, so we don't generate get a large plastic deformation. And the third type is a hyperelastic material. In hyperelastic material, the material returns to its original shape after being unloaded. And in other words, when these materials are unloaded, the internal energy stored in them in the elastic regime is fully recovered. And the models that simulate a hyperelastic behavior can address elastic large strain behavior in rubber, field elastometers, biological tissues, and the other type of rubbery material. So as you can see in the curve that we have here, is some sort of, you have like it is some like you have a two section. So one section that it reaches the some sort of like a critical point, and again you will have another one that it's going to go up due to a densification in the material. So these are basically a tensile test that we have. So in Abaqus we can model these type of material by going to property and mechanicals, plasticity, and hyperelastic. And here, as you can see, we have a different type of strain energy potential or methods that are introduced by different scientists, and which will have a constant for each of them. So if I go to coefficient, you'll see that each method has its own basically coefficient that you need to put to basically simulate that hyperelastic behavior in Abaqus. So currently we are using isotropic material, so it's not anisotropic. And what we're going to do, we're basically going to import test data from experimental result. So as you can see here, we have a different type of test that we can use to get this coefficient that I'm going to show you in the next slide. So there are different type of experimental tests that you can do to obtain appropriate stress strain curve that you can use it as an input for Abaqus to extract those coefficient for a selected hyperelastic model. So the basic one is basically a uniaxial test data. It can be in tension, or it can be in compression, and you can have a planar test data, volumetric test data, or biaxial test data. And as I showed you, we have different type of model for hyperelastic material in Abaqus, and each of them will use a specific strain energy potential. So as you can see, each of them will give you the specific constant which is related to that strain energy potential equation, which Abaqus will use to simulate that hyperelastic behavior for your model. Okay, so what I'm gonna do, I will basically make these model in Abaqus. So first of all, I'm going to evaluate a material property and find the coefficient for experimental data. Then I will use that experimental data that it came from this ISO 37 tensile test sample to run a model to see that how accurate is my material model. Right. Before making a part in Abaqus, first of all, we have to evaluate hyperelastic properties to find the best material model. As I mentioned, that there are different type of material model, but not all of them are suitable for the material that you have. So when you do experimentals, and it doesn't necessarily mean that you can use all of these, material model. You have to pick the best one. So how are we going to do that? By evaluating the material input. So let's create a material, and at the top I would say this is basically, this result comes from the flexible adhesive. So I will call this one flexible adhesive, and I'm going to go to mechanical elasticity elastic. So, and sorry, not elastic, I'm going to go elasticity hyperelastic. And here I don't know which strain energy potential that I'm going to use, because I don't have any idea which of them is the best fit for my experimental data. So in order to find that, I'll keep this one as unknown, and I'll go to a test data, and I have the data for tensile testing. So I'm going to go to uniaxial test data, and as you can see here, what I can do, I can add nominal stress and nominal strain to here. So from resources section, if you go to if you download it, you'll see that you'll have this stress strain data is a stress strain data that comes from experiment. So copy this one and basically paste it here and click on OK. So I'm done with this one, so I'll click on OK. As you can see, I have this flexible adhesive here. Then I'm going to right click on this one and evaluate basically my input data. And so first of all, I have to select the test that I imported the data. So this is going to be uniaxial, so I'm going to deactivate this one and this one, and I'm going to say the minimum strain, I'll say 0, I don't want it to be negative, and the maximum strain that I will automatically select it from the input data. So we're done with this one. So basically I said the source is the test data and is uniaxial because I don't have the other one, and then I will use the strain energy potential, and here is the place that we can basically select the material model. So as you can see, we have a different strain potential energy, and from here we can select the material model. Generally, we go for a polynomial and origin number 3, and I normally use the no-hook and Aruda-Boise, and these are the one I generally use for the initial assessment. However, when you have a specific material, you have to definitely check in literature and see what is the most suitable fit for that specific material. So it doesn't necessarily mean that what I selected here is going to be suitable for yours. So it's, before doing this type of assessment, it's better to always check literature to see what other people has done and how is the fit for their model. And based on that, you can judge what it's going to be the best model for yours. And obviously you can select all of them and assess all of them, but it's not necessarily a good practice. So it's always better to check in literature and find a suitable one. Okay, so I selected this one, reduced polynomial and Aruda-Boise, and I'm going to click on OK. Okay, so the following characters are not allowed in the name of being evaluated. So I think the problem is that I had space here. So I will just do this one, click on OK, and evaluate this. Cancel all of these, make this one 0. Strain energy, I'll keep this one and this one, click on OK. So Abacus doesn't normally like space. So it's better when you want to write a tune, I always put a dash between them. Wait for Abacus to assess the property, and here we'll have these material model that we have selected. So for the first one, you see that it tells us it's unstable. So unstable at nominal strain larger than this value. So for uniaxial tension, same for compression. So basically Abacus will assess this material model for a different basically test condition. I will tell you that it's only stable fully for volumetric tension and volumetric compression. So we're not going to use this one. The second one here, again the same scenario. So you see that is unstable for these ones, and but is stable for volumetric tension and compression. And then no model, as you can see, is stable for all the conditions. So this is one of the technique, one of the material model that we can use. And the second one is the same thing. So as you can see here, this one is stable as well. So we can use this one for our simulation. So what you need to basically do, you need to write down these coefficient, because obviously when you do a simulation, when you do an experiment and you want to use this experimental data for your model, imagine you get a piece of rubber and you go and do a test, but the application is something less. Let's imagine the application is the car's tire, and obviously when you're in a team of engineers, you don't really want to send the experimental data. What you can do, you can share with them this coefficient, and this coefficient will represent your experimental data. Okay, so it's much easier to put these coefficient in your report rather than putting a large experimental data in your appendix. So what I did, I recorded these values for both technique, that I'm going to use one of them for our example. So I'm going to dismiss this, and if I go to test data, so this is my test data, and these are the ones. So let's hold the control, select the test data and the first one, and click on plot. So first of all, I have to minimize this, because this is basically that comes from the our assessment for a material property, or we can actually close it. And then here, if I select the first one and this one, click on plot, you see that how close is the coefficient result in comparison to the test result. The test result is coming from here, and that's the experiment. The top one is basically the triangle one is the coefficient result, and the red one is the experimental result. So you see that it's very close. And so let's see this one. So let's see these two. Again, the same thing. So this is another acceptable result. So if I compare these three, you see that I think they're quite close, but the orange color is Aruda Boys is more closer fit to experimental data. So basically, what I'm going to use this model for the example that we're going to do. Okay, so this is our assessment. Now let's imagine that we don't have experimental data, and the engineering team in the experimental section passed us this coefficient that we got. They got from experiments. So they said they did a test, and these are a coefficient. So first of all, before we use those for the project, we want to verify if what they got is correct. And we know that they used this dog bone shaped sample. So what we want to do, we basically want to see if we do the same geometry and we put these coefficient as a material property, we can get the experimental data result. So now go to property, create a part, and let's do 2D, deformable shell, and the approximate size is okay to be 200. And let's create a two construction line. And what I'm going to do, I'm going to fix these, and also the bottom one. And then I'm going to draw one line from here to here, and another line from here to here. So from here to here, I know that it's 21 divided by 2, so is 10.5. And I know this one is basically 25 divided by 2, that's 12.5. Let's see if why this one doesn't show the 5, so I'm just gonna double check. So that's 10.5. Yeah. So now we're gonna go back to this section. So as you can see, we have one arc here is 25, and another arc at the bottom 11. So two arc is touching each other, and basically they have a tangent to the line at the top and the tangent line to the bottom and also in the middle. This is a tricky part too, and if you make a mistake probably you're not going to get this right, because you actually don't have the dimension of this straight line here, and you have to model that correctly, otherwise it's not going to be right. And we know that the total distance is 100, so from the middle to top is 50. So what I'm going to do, I'm going to give that dimension as well, so that's going to be 50. And I know that from here to here is basically 2.5, and to be honest I think that this is a little bit long, so I'm gonna just get rid of these and draw a smaller line, let's say up to here, and then I'm gonna use this arc and I'm gonna draw one line from here to here like this, and another arc from here to here like this. Okay, and then I'm gonna go to constraint and use a tangent. Tangent, and select this one and this one, so these are tangent, and this one to this one is a tangent, and this one to this one is a tangent. Okay, now is the time to give a dimension to this one, so that's going to be 25 and that's going to be 11. Okay, so now as you can see we have the green one here, which means that the dimension is correct. So if you by mistake you give a dimension and you try to tangent them later, you might struggle. So it's really important to set the dimension that you already know, like the 50, 10.5, 2.5, and you know that these are tangent, and do them there, and then give a dimension to these arc. So I've done a 1/4 of this, so I can do a mirror to the other side. So if I use the mirror command, and it will ask me select the type of the mirror, is going to be copy because I want to keep it, and it say pick a mirror line, which is going to be the middle, and then select the lines. It's going to be this one, click on OK. So I have this in this direction done, and then so what I'm going to do now, so what I'm going to do, I'm going to mirror this one again to the bottom, so select this one again, again it's going to be copy, select this line, done. Sorry, I need to select the line, so it's going to be this line, this one, and hold the shift to the other side and click on done. So I have it on both sides, and click on done, done. So we have this dog bone shape sample, which is based on ISO 37 standard. Okay, so next step is going to property, and in property I'm going to create a new material property. I'll just call it new flexible, and here I'm going to go to mechanical hyperelastic, and so from here I'm going to select the Boys, and instead of test data I'm going to use the coefficient, and let's get those value from the, so it's the first one, so I need this one, and also these ones. Okay, and click on OK, and I have to actually get rid of these, or when I edit them I have to say okay, this is our boys. Otherwise, even if you don't use these material in your model, what will happen, that Abacus will give you an error that you haven't selected which type of strain energy potential you're going to use. Although you're not actually using this for a simulation, but for some reason Abacus doesn't like that you don't select. So once you assess this one, you can just get rid of it. So I generally remove this one because I don't need it anymore after assessment. So this is the new flexible that I have in assembly. Simply just import your model as a part, and it's going to be mesh on a part, step, create a step, and static, and let's turn on a non-linear, make this one here, and 0.1, and this one 15, click on OK, and then we go to interaction here. Because we're going to apply displacement, what I want to do, I don't want to apply displacement on the line, as I mentioned, especially if you have a large deformation. Then what will happen basically is that you're gonna deform, you're going to have a mesh distortion on the edges. So let's create a node, reference point node, so we can couple this one to this line. So if I go to tools, first of all, let's just create that pointer. So I'm going to go to part, and from the point here, I'm going to move this one, let's say 0, 5, 0, and then I'm going to give a reference point to it. And what else I'm going to do? I'm going to go back to interaction, and I'm going to use coupling basically. So I'm going to couple this one, and node region, I'm going to select this one and this one, click on OK, and done. So basically what happens to this node, it will happen to that line. And then go to load, and fix the bottom one. So I'm going to do that in initial, so it's going to be fixed in all directions. And the same thing for the top. I'm going to apply displacement in initial steps, so everything in initial step is 0. And then I'm going to go here, edit this in a propagated step 1, and I say that in step 1 we'll have 2 millimeter displacement in a positive direction, in Y direction. Click on OK. I just realized that this is like a kind of flexible, and 2 millimeter is very small, so let's just make this one let's say 25 millimeter instead, because of the nature of the rubber type material, you're going to have very large deformation, and in 2 millimeter basically you're not going to have a much movement. So click on OK, and the next step is going to mesh, and we have to apply a mesh to here. Because we imported as a dependent, we have to go to part, and as you can see here, we cannot apply a structure mesh, I guess. So if I go to structure, let's see. Oh yeah, we can. Okay, so we can apply a structure mesh to this one, but for any reason, if you cannot, then you have to create a partition basically from here to here, as you can see, and from then you have another node here to here, and from here to here. Probably if you make this one in 3D, you would notice that you cannot apply a structure mesh, and you have to create a partition. So let's apply a mesh to this one and make it, let's see how good is the default mesh. I think I'm happy with this one, and then assign a mesh, yes. And yeah, this is not too bad. What we want to have a more dense mesh in the middle in comparison to the other part, because failure generally happen in those areas. Okay, so that's everything. Okay, so now I'm going to go back to do a check if I've done everything correctly. So the part is, yeah, simple. Property, oh yeah, so this is a here that I forgot actually to assign a property. So what I have here, I've created this new flexible, I didn't create a section for it. So I'm going to create a section, and I'm going to call this one again new flexible, homogeneous, continue. And here again I will activate this one because it's in 2D, and the thickness is 2 millimeter in a Z direction. So click on OK, and assign this one to the geometry. Click on done. Then we have assembly, again straightforward step, we don't have to do anything here. Interaction, we did coupling, and in load we fixed the bottom, we apply the displacement to the top, and in the mesh section we created a mesh. Okay, so now let's create a new job. I'm going to minimize this one and create a job. I'm going to call this one flexible, let's call it same, new flexible, and it's going to be model 1, continue, click on OK, and submit the job. So if I have done everything correctly, it should be a quick simulation. Yeah, as you can see, it's done after 6 increments. Let's just see the result. And if I apply this one, you see that how the material will basic stretch in the result section. So this is basically 1 misses, and if I go to displacement, you see that the maximum displacement that we have at the top there is at 25. And also what I can also do is to extract some sort of load, and I can do that by going to create ODB field output, click on continue, and I can go to unique nodal element, delete selection, and add selection. I know that my node is located somewhere there, so I'll just create a big rectangle, and as you can see I have the node selected. Click on done at the bottom, and then go here, select the magnitude of reinforcement and displacement magnitude, and click on plot. So that's basically what I have for this material, which is the force, and also I have a displacement for it. Okay, so I'm going to save these data, click on OK, and I have them as U and RF. It's this one, yeah, these two. So I can combine them together to create a force displacement by going to operate on a XY data. Click on continue, say combine, and select U as a displacement and RF as a force. Plot this one and save the data as a load displacement. Click on OK. So this is basically a load displacement data that we have, but bear in mind that this is basically force displacement, so you cannot actually compare this one with the stress strain data that we had in Excel file. So this result that you get, you have to compare this with the experimental data that you get from a tensile test machine, and if you are using any sort of non-contact measurement to measure displacement, or even you can use the crosshead data, because the displacement is quite large, so slipping is not going to really affect the result that much. So once you compare the force displacement with the experimental force displacement result, and if they match, then you're confident enough that the material model that you created, these new coefficients, are they can represent a hyperelastic behavior, and then you can use that for any sort of any sort of simulations or application. Thank you so much for watching this video, and I hope you enjoyed it, and I hope to see you in the next video. Thank you.